For decades, we believed we understood our motion through space. Earth spins, we orbit the sun. The sun travels through the galaxy. Simple, predictable, contained. But here's what will blow your mind. Right now, as you sit there, you are racing through the universe at over 2 million miles per hour towards something so massive, so distant, that we only discovered what it was in the last decade. This isn't expansion. This is actual movement through space, a cosmic current carrying our galaxy and thousands of others toward a destination that challenges everything we thought we knew about the structure of the universe. If you want to understand where we're really going and what's pulling us there, hit that like button and subscribe. This is the story of the greatest journey you never knew you were taking. Prepare yourselves. Let's begin. Right now, at this very moment, you are moving. Not metaphorically, not philosophically. Physically, measurably, undeniably moving through space at a velocity so extreme that if you could somehow step outside your motion and watch yourself pass by, you would see yourself cross the distance from Earth to the Moon in less than 7 minutes. 2 million miles per hour. Let that sink in. 2 million miles per hour is not a speed humans can intuitively grasp. A commercial jet flies at about 570 miles per hour. The fastest car ever built topped out at just over 760 miles per hour. The Apollo astronauts, the fastest humans in history, traveled at roughly 25,000 miles per hour on their way to the Moon. You, sitting in your chair, are moving 80 times faster than that. But toward what? That's the question. That's the mystery that has consumed astronomers for nearly a century. Because we can measure this motion with extraordinary precision. We can calculate it, verify it, map it across the sky. What we couldn't do, until very recently, was explain it. We didn't know what was pulling us. We just knew something was out there, something so massive that its gravity reaches across hundreds of millions of light years to drag our galaxy through space like a leaf caught in a river current. To understand where we're going, we need to understand all the ways we're already moving. Because that 2 million miles per hour figure isn't one motion. It's the sum of multiple motions stacked on top of each other. A hierarchy of cosmic velocities that operates on scales from planetary to intergalactic. Start with the most familiar, Earth's rotation. If you're standing at the equator, you're moving east at roughly 1,000 miles per hour. That's the speed required to complete one full rotation every 24 hours. Move toward the poles, and that speed decreases down to 0 at the exact rotational axis. This is why hurricanes spin the way they do, why long-range artillery has to account for the Coriolis effect, why the Earth bulges slightly at its middle. We live on a spinning sphere, and that spin is real motion through space. But Earth isn't just spinning, it's also orbiting. Our planet circles the Sun at an average speed 67,000 miles per hour, completing the journey once every 365.25 days. We travel in an ellipse, not a perfect circle, which means our speed varies slightly throughout the year. Faster when we're closer to the Sun in January, slower when we're farther away in July. The total distance of one orbit is about 584 million miles. We cover that distance every single year, and we barely notice. Now zoom out further. The Sun itself, dragging Earth and all the other planets with it, is moving through the Milky Way galaxy. Our solar system orbits the galactic center at roughly 514,000 miles per hour. At that speed, it takes us approximately 230 million years to complete one full orbit. The last time we were in this position in the galaxy, dinosaurs were just beginning to dominate Earth. 1 galactic year from now, if humanity still exists, we will be a species unrecognizable from what we are today. But we're not done, because the Sun isn't just orbiting the center of the Milky Way in a neat circular path. It's also bobbing up and down through the galactic plane, oscillating above and below the disk of stars, like a horse on a carousel. This vertical motion adds complexity to our trajectory, a sine wave overlaid on a spiral. Every 33 million years or so, we pass through the densest part of the galactic disk, increasing our exposure to cosmic rays, supernovae, and gravitational perturbations from passing stars. Some scientists have even suggested that these passages might correlate with mass extinction events on Earth, though the evidence remains controversial. And still, we're not done. Because all of that motion, the rotation, the orbit around the Sun, the Sun's path through the galaxy, all of it is happening inside a galaxy that is itself moving. The Milky Way, along with the Andromeda Galaxy, and about 50 other smaller galaxies that make up what astronomers call the local group, is traveling through intergalactic space at approximately 1.3 million miles per hour. This is not the expansion of the universe carrying us passively along. This is peculiar velocity, real motion through space relative to the cosmic microwave background radiation, the afterglow of the Big Bang itself. Add up all these motions, account for their directions, do the vector mathematics. The result is staggering. Roughly 2.1 million miles per hour in a specific direction in the sky, toward a region in the constellation Centaurus. For decades, astronomers have known about this motion. They've measured it with increasing precision using everything from radio telescopes to satellites. But measuring the motion was the easy part. Understanding why we're moving, identifying what's pulling us, that took decades of detective work, false starts, and paradigm-shifting discoveries. Because here's the thing about gravity. It's weak, but it's relentless, and it has infinite range. Every mass in the universe attracts every other mass. You're gravitationally bound to the chair you're sitting in, to the Earth beneath you, to the Sun, to the center of the Milky Way, to the Andromeda Galaxy, to structures millions and even hundreds of millions of light years away. Gravity doesn't stop. It just gets weaker with distance, following the inverse square law. Double the distance, quarter the force. So when astronomers measured our motion and found us rushing through space at over 2 million miles per hour, they knew it meant something out there, something incomprehensibly massive, was pulling us. The question was, what? And perhaps more importantly, how far away is it? And are we ever going to get there? The answer would require mapping the universe on the largest scales ever attempted. It would reveal structures so vast they barely fit inside the observable universe. And it would force us to confront the unsettling reality that even on cosmic scales, we are not in control of our destiny. We are passengers on a journey that began billions of years ago and will continue billions of years into the future, racing towards something we're only just beginning to understand. The breakthrough came not from looking at galaxies or stars, but from looking at nothing, or rather, at what we thought was nothing. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were trying to eliminate a persistent hiss from their antenna at Bell Labs in New Jersey. No matter where they pointed their horn-shaped receiver, no matter what time of day or night, there was always this faint, annoying static. They checked everything. They cleaned out pigeon droppings from the antenna. They recalibrated their instruments. The noise remained. What they'd stumbled upon, completely by accident, was the cosmic microwave background radiation, the CMB, the afterglow of the Big Bang itself, cooled over 13.8 billion years from the white-hot plasma of the infant universe to just 2.7 degrees above absolute zero. It fills all of space. It comes from every direction equally. It's the oldest light in the universe, released when the cosmos was only 380,000 years old and finally became transparent. Penzias and Wilson won the Nobel Prize for this discovery. But the CMB held more secrets than anyone initially realized. In the early 1970s, astronomers began measuring the CMB with greater precision, and they noticed something strange. The radiation wasn't perfectly uniform. When they looked at the sky in one direction, the CMB was slightly hotter, shifted very slightly toward shorter wavelengths, toward the blue end of the spectrum. When they looked in the opposite direction, it was slightly cooler, shifted toward longer wavelengths, toward the red. The difference was tiny, less than 1 part in 1,000, but it was real, and it was consistent. This pattern is called the dipole anisotropy, and it's caused by the Doppler effect, the same phenomenon that makes an ambulance siren sound higher pitched as it approaches you and lower pitched as it moves away. Light works the same way. If you're moving toward a source of light, the wavelengths get compressed, blue shifted. If you're moving away, they get stretched, red shifted. The dipole in the CMB meant we were moving, not Earth around the Sun, not the Sun around the galaxy. We're talking about our motion through the universe itself, relative to the CMB, which represents the closest thing physics has to an absolute reference frame. In 1992, NASA's Cosmic Background Explorer satellite, COBE, measured this dipole with unprecedented accuracy. The results were definitive. The local group of galaxies, which includes the Milky Way, Andromeda, and about 50 smaller galaxies, is moving at 627 kilometers per second. That's about 1.4 million miles per hour. The direction? Toward galactic coordinates longitude 276 degrees, latitude 30 degrees. In layman's terms, toward a region of sky in the constellation Hydra, but really encompassing parts of Centaurus and Vela as well. This was extraordinary. The CMB dipole gave astronomers a cosmic speedometer. For the first time, they could measure our true motion through the universe, not relative to the Sun or the galaxy, but relative to the fundamental reference frame of space-time itself. But here's the critical question. Why are we moving? The universe is expanding. Edwin Hubble proved that in 1929. Distant galaxies are receding from us, and the farther away they are, the faster they're moving. But that expansion is smooth and uniform on large scales. It carries everything along together. It shouldn't produce a net motion in one particular direction. The dipole anisotropy revealed that we have a peculiar velocity, motion over and above the expansion of space. We're not just being carried along passively, we're being pulled. Something out there, something with enormous mass, is exerting a gravitational tug strong enough to accelerate our entire local group to more than 600 kilometers per second. Think about what that means. Gravity falls off with the square of distance. To pull us at this speed, the source has to be either relatively nearby and moderately massive, or extremely distant and unimaginably massive. Either way, we're talking about a concentration of matter large enough to influence the motion of thousands of galaxies across hundreds of millions of light years. The CMB dipole was a clue. It told us we were moving and in what direction, but it didn't tell us what we were moving toward. For that, astronomers needed to map the distribution of galaxies in 3 dimensions, measure their velocities, and trace the gravitational flows that govern motion on the largest scales. This work began in the 1980s and continues to this day, and what it revealed was a universe far stranger, far more structured, and far more dynamic than anyone had imagined. The story of what's pulling us involves not one massive object, but a hierarchy of structures, each larger and more massive than the last, nested inside one another like Russian dolls made of galaxies. And it starts close to home, with our nearest galactic neighbor. Andromeda is coming for us. Not metaphorically, not eventually. Right now, at this moment, the Andromeda galaxy is rushing toward the Milky Way at approximately 110 kilometers per second. That's about 246,000 miles per hour. In cosmic terms, it's a collision in slow motion. But it's happening, and it's inevitable. The Andromeda galaxy, also known as M31, is the nearest large galaxy to our own. It sits about 2.5 million light-years away, which means the light we see from it tonight left before humans existed on Earth. Despite that distance, Andromeda dominates our local cosmic neighborhood. It's bigger than the Milky Way, containing roughly 1 trillion stars compared to our 200 to 400 billion. Its mass is estimated at about 1.5 times that of our galaxy. When you look up at the night sky on a clear, dark night, away from light pollution, Andromeda appears as a faint smudge, a ghostly oval. What you're seeing is the combined light of 1 trillion suns, so distant that it takes over 2 million years to reach your eyes, and it's heading straight for us. The Andromeda galaxy and the Milky Way are the 2 dominant members of what astronomers call the local group. This is our immediate galactic neighborhood, a gravitationally bound collection of more than 80 galaxies spanning roughly 10 million light-years. Most of these galaxies are dwarfs, small irregular collections of stars with masses ranging from a few million to a few billion solar masses. The 3rd largest member is the Triangulum galaxy, M33, a spiral galaxy about 60,000 light-years across with perhaps 40 billion stars. It sits about 3 million light-years from us, and its ultimate fate is tied to the dance between the Milky Way and Andromeda. Then there are the Magellanic Clouds. The large and small Magellanic Clouds are satellite galaxies of the Milky Way, visible from the southern hemisphere as bright patches in the night sky. The Large Magellanic Cloud contains about 30 billion stars and orbits our galaxy at a distance of about 160,000 light-years. These aren't just companions. They're captives, bound by our gravity, and astronomers now believe they're being slowly torn apart and consumed by the Milky Way over billions of years. The local group is a family, but it's a dysfunctional one. Everything in it is moving, orbiting, colliding, merging. It's a microcosm of galactic evolution, and it tells us how galaxies grow. Andromeda and the Milky Way have been falling toward each other for billions of years. They likely formed from the same initial density fluctuations in the early universe, condensing out of the primordial soup of matter roughly 13 billion years ago. For a time, as the universe expanded, they moved apart, but eventually, their mutual gravity overcame the expansion, and they began falling back together. The math is straightforward, but the implications are profound. Andromeda's blue shift, the compression of its light toward shorter wavelengths, tells us it's approaching. For decades, astronomers weren't sure if this approach would result in a direct collision or if Andromeda might pass by at a safe distance. That uncertainty existed because measuring transverse motion, the sideways component of velocity, requires incredibly precise measurements of how an object shifts position against the background sky over many years. Galaxies are so far away that this proper motion is vanishingly small. In 2012, using data from the Hubble Space Telescope accumulated over 7 years, astronomers finally nailed down Andromeda's trajectory. The result was definitive. Andromeda's sideways motion is essentially zero. It's headed almost directly toward us. Collision is inevitable. The timeline? The first close passage will occur in about 4 billion years. At that point, the two galaxies won't immediately merge. They'll pass through each other, their stars so widely spaced that actual stellar collisions will be extraordinarily rare, but their dark matter halos will overlap. Gravitational forces will distort both galaxies, pulling out long tidal tails of stars. Gas clouds will collide, triggering massive bursts of star formation. The night sky, if anyone is around to see it, will be spectacular and terrifying. Andromeda will dominate the sky, a swirling maelstrom of billions of stars stretched across the heavens. After the first pass, the two galaxies will swing back around, their orbits decaying as dynamical friction. The gravitational drag from their halos saps their energy. A second collision, more violent than the first. Then a third. Over the course of perhaps 2 billion years, the Milky Way and Andromeda will spiral into each other, their stars mixing, their supermassive black holes eventually merging at the center. The final product will be a giant elliptical galaxy, a smooth ball of stars with little gas left for new star formation. Astronomers have given this future galaxy a name, Milkomeda, or Milkdromeda, depending on who you ask. Our Sun, if it still exists, will likely be flung to the outer regions of the merged galaxy, residing tens of thousands of light years from the new center. But the Sun will be near the end of its life by then anyway, swelling into a red giant and consuming the inner planets, including Earth. But here's the critical point. This local drama, this cosmic collision between Andromeda and the Milky Way, doesn't explain our motion through the universe. The Andromeda-Milky Way approach is mutual. We're falling toward each other. That motion is internal to the local group. It doesn't account for the fact that the entire local group is moving at over 600 kilometers per second relative to the cosmic microwave background. That velocity comes from something else, something much larger and much farther away. The local group is not isolated. It's part of a larger structure, and that structure is falling towards something even bigger. To understand our true trajectory through the universe, we have to zoom out, way out. 55 million light years away, in the direction of the constellation Virgo, lies the nearest major galaxy cluster to us, the Virgo cluster. It's enormous. Over 2,000 galaxies packed into a region about 15 million light years across. To put that in perspective, the local group contains about 80 galaxies spread over 10 million light years. Virgo crams 2,000 galaxies into a slightly larger volume. It's a different class of structure entirely. The Virgo cluster dominates our local universe. Its center is anchored by 3 giant elliptical galaxies, M87, M86, and M49. M87 alone contains several trillion stars and harbors one of the most massive black holes ever directly observed, weighing in at about 6.5 billion times the mass of our Sun. This black hole is so massive and so active that it shoots jets of superheated plasma thousands of light years into intergalactic space, visible to radio telescopes as brilliant beacons of synchrotron radiation. But the visible galaxies are just the tip of the iceberg. The Virgo cluster is embedded in an enormous halo of dark matter, invisible material that interacts only through gravity. This dark matter halo contains perhaps 10 times more mass than all the visible stars and gas combined. And it's this dark matter that gives the cluster its immense gravitational pull. We're falling into it. The local group, along with dozens of other nearby galaxy groups, is being pulled toward Virgo at approximately 300 kilometers per second. Astronomers call this Virgo-centric infall. It's been known since the 1970s, when surveys of galaxy distances and velocities first revealed a systematic pattern. Galaxies near us, on the side toward Virgo, are moving slower relative to the cosmic expansion than they should be. Galaxies on the opposite side are moving faster. The pattern is exactly what you'd expect from gravitational infall toward a massive object. But here's the twist. We're not going to reach Virgo, not in any meaningful time frame. The universe is expanding. Edwin Hubble discovered this in 1929, and subsequent observations have refined the measurement. The expansion rate, called the Hubble constant, is about 70 kilometers per second per megaparsec. That means for every megaparsec, roughly 3.3 million light years, the recession velocity increases by 70 kilometers per second. Virgo is about 16.5 megaparsecs away. At that distance, the expansion of space is carrying it away from us at roughly 1,200 kilometers per second. Our infall velocity toward Virgo is only about 300 kilometers per second. We're losing the race. We're falling toward Virgo, but we're not falling fast enough to overcome the expansion of space. We'll never actually get there. Think of it like a treadmill. You're running toward a destination at 300 kilometers per second, but the treadmill itself is moving backward at 1,200 kilometers per second. You're running as hard as you can, but you're still moving away from your goal. That's our situation with Virgo. But Virgo-centric infall is important because it tells us we're part of a larger structure. The local group isn't isolated. We're part of what used to be called the local supercluster, also known as the Virgo Supercluster. This is a flattened, disk-like collection of galaxy groups and clusters spanning about 110 million light-years, all gravitationally associated with the Virgo cluster at its heart. For decades, astronomers thought the Virgo supercluster was our largest gravitational home. The prevailing model was that we were on the outskirts of this structure, slowly falling toward its center. Our motion through the universe was explained as the combination of this infall plus the gravitational pull from more distant structures. But there was a problem. The numbers didn't add up. The CMB dipole tells us we're moving at 627 kilometers per second relative to the cosmic microwave background. Virgo-centric infall accounts for only about 300 kilometers per second of that motion, and it's not even in quite the right direction. There's a significant component of our velocity that points well beyond Virgo, toward a region of sky in the constellations Centaurus and Hydra. Something else is pulling us, something much bigger than Virgo, something so massive that its gravity reaches across hundreds of millions of light years. In the 1970s and 80s, astronomers began mapping the three-dimensional distribution of galaxies across larger and larger volumes of space. They used redshift surveys, measuring how much the light from each galaxy was stretched by the expansion of the universe to determine its distance. Build up enough measurements, and you can create a map of where all the galaxies are. What they found was structure. The universe isn't smooth. Galaxies clump together into groups and clusters. Clusters clump together into superclusters, and superclusters are arranged in filaments and sheets, surrounding vast empty regions called voids. It's often described as looking like foam or a sponge, a cosmic web of matter with most of space being empty. But they also found something else, something unexpected. When they measured the peculiar velocities of galaxies, the component of their motion not caused by the expansion of the universe, they found coherent flows, streams of galaxies moving together in the same direction across enormous distances. It wasn't random, it was organized. Galaxies hundreds of millions of light years apart were participating in the same large-scale motion. This could only mean one thing. There was structure we weren't seeing. Concentrations of mass large enough to influence the motion of galaxies across a significant fraction of the observable universe, and we were falling toward one of them. In 1973, astronomers noticed something strange. Galaxies in our cosmic neighborhood weren't moving the way they should. According to Hubble's law, galaxies should be receding from us smoothly, with velocity proportional to distance. But when astronomers measured the velocities of nearby galaxies carefully, accounting for their distances, they found systematic deviations. Galaxies in certain directions were moving too fast. Galaxies in other directions were moving too slow. The pattern suggested something massive was pulling them, but the data was sparse and the implications were uncertain. It would take another decade of painstaking observations before the picture became clear. In the 1980s, a team of astronomers, led by Alan Dressler and including Sandra Faber, Donald Lyndon Bell, and 4 others, who became known as the Seven Samurai, embarked on an ambitious project. They would measure the distances and velocities of hundreds of elliptical galaxies, building up the most detailed map yet of peculiar velocities in the nearby universe. Elliptical galaxies were chosen because they follow a tight relationship between their luminosity and how fast their stars are moving internally. Measure one, and you can infer the other, giving you a distance estimate independent of redshift. The results were shocking. The data revealed a massive flow of galaxies, all moving in roughly the same direction at speeds of several hundred kilometers per second. The Milky Way, the Virgo cluster, the Hydra Centaurus supercluster, dozens of other galaxy groups and clusters, all streaming together toward a single region of space. In 1987, Dressler gave this mysterious gravitational anomaly a name: the Great Attractor. The Great Attractor is located about 220 million light-years away from us, in the direction of the constellations Triangulum Australe, Norma, and Centaurus. And here's the cruel irony. It sits almost directly behind the plane of the Milky Way. When we look in that direction, we're looking through the densest part of our own galaxy, through clouds of dust and gas so thick they block visible light. Astronomers call this region the zone of avoidance. It's a blind spot, a cosmic curtain that hides a significant fraction of the nearby universe from our view. But we can infer what's there from the motion it causes. The Great Attractor contains a mass equivalent to tens of thousands of Milky Way galaxies, all concentrated in a relatively small region of space. Its gravity is so strong that it's pulling us, along with hundreds of thousands of other galaxies, toward it at about 600 kilometers per second. That's over 1.3 million miles per hour. To give you a sense of scale, imagine you could see all the galaxies in our region of the universe, color-coded by their velocity. Galaxies between us and the Great Attractor would be blue-shifted, moving toward it. Galaxies on the far side would be red-shifted, moving away from us, but still falling toward the attractor. Galaxies to the sides would have velocities at an angle. The pattern would be unmistakable. Everything is falling toward this one spot. But what exactly is the Great Attractor? For years, that question had no satisfying answer. The zone of avoidance made direct observation nearly impossible. Optical telescopes were useless. The dust scattered and absorbed visible light. Astronomers had to turn to other wavelengths. X-ray observations in the 1990s revealed the Norma cluster, a massive galaxy cluster sitting right where the Great Attractor should be. Designated Abell 3627 in the Abell catalogue of rich clusters, Norma is a monster. It contains thousands of galaxies embedded in a halo of hot gas, glowing at millions of degrees. The total mass is enormous, at least 10 to the 15 solar masses, mostly in the form of dark matter. Then, in 2016, radio astronomers using the Parkes telescope in Australia managed to peer through the zone of avoidance by observing neutral hydrogen, which emits radio waves at 21 centimeters. They discovered hundreds of previously unknown galaxies hidden behind the Milky Way, including several massive clusters and superclusters. The picture started coming together. The region of the Great Attractor isn't just the Norma cluster. It's a vast supercluster, an overdense region containing multiple massive clusters spread across tens of millions of light years. But even as the Great Attractor came into focus, a new mystery emerged. Because the Great Attractor, as massive as it is, isn't massive enough. The peculiar velocity of the local group is 627 kilometers per second. The Great Attractor can account for some of that motion, maybe even most of it if you're generous with the estimates. But the numbers don't quite work. The direction isn't quite right. Our velocity vector points somewhat beyond the Great Attractor, towards something farther away. And then there's the uncomfortable fact that the Great Attractor itself is moving. Observations in the 1990s revealed that the entire Great Attractor region, including all its galaxies and clusters, is flowing in the same general direction as us. It's not the final destination. It's a waypoint. We're falling toward the Great Attractor. But the Great Attractor is falling toward something even bigger. Something so massive that it dominates the gravitational landscape of our entire corner of the universe. Something that wouldn't be properly understood until the 21st century, when astronomers finally mapped the cosmic web in unprecedented detail and discovered the true scale of the structures we're embedded in. The Great Attractor was just the beginning. In September 2014, a team of astronomers led by R. Brent Tully from the University of Hawaii published a paper in the journal Nature that fundamentally changed how we understand our place in the universe. They had spent years compiling what they called the Cosmic Flows 2 Catalog, a database of peculiar velocities for over 8,000 galaxies within a radius of about 300 million light-years. Peculiar velocities are the motions of galaxies above and beyond the expansion of the universe, the real movement through space caused by gravitational attraction and repulsion. But they didn't just collect data, they developed a new technique for analyzing it. Instead of looking at where galaxies are, they looked at where galaxies are going. They mapped the flow of galaxies through space, like mapping ocean currents or river systems. And just as rivers flow downhill toward the ocean, galaxies flow along gravitational gradients toward massive structures. When you map flows, you can identify watersheds. On Earth, a watershed is a boundary where water on one side flows toward one river basin, and water on the other side flows toward a different basin. The same concept applies to galaxies. There are regions of space where galaxies on one side are flowing inward toward a particular structure, and galaxies on the other side are flowing outward toward different structures. These boundaries define basins of attraction. What Tully and his team discovered was that the Milky Way, the Virgo cluster, the Great Attractor, and dozens of other major structures are all part of the same basin of attraction. We're all flowing toward the same gravitational focal point. The entire region, everything flowing inward together, comprises a single, coherent superstructure, and it's enormous. They named it Laniakea, a Hawaiian word meaning immense heaven. The Laniakea Supercluster is 500 million light-years across and contains the mass of 100 quadrillion suns, written as 10 to the 17th solar masses. It encompasses roughly 100,000 galaxies, including our own. Its center of mass, the gravitational focal point, where all the flows converge, is the Great Attractor. Let me repeat that because it's important. The Great Attractor isn't some mysterious separate entity. It's simply the name we gave to the center of mass of Laniakea. It's the downtown core of our supercluster, the gravitational heart, where the density of galaxies and dark matter is highest. We've been falling toward the Great Attractor because we've been falling toward the center of our own supercluster. Laniakea consists of 4 major components. The first is the Virgo Supercluster, which includes our local group and the Virgo cluster. The second is the Hydra Centaurus Supercluster, a massive collection of galaxy clusters in the southern sky. The third is the Pavo Indus Supercluster, another southern feature. And the fourth is the Southern Supercluster, which includes the Fornax cluster and other major structures. Together, these regions form a flattened, somewhat elongated structure, with the Great Attractor region at the center of mass. But here's the crucial insight. Defining Laniakea required mapping not just positions, but velocities. Previous definitions of superclusters were based on overdensity, regions where galaxies were more tightly packed than average. The problem with that approach is that it doesn't tell you whether the structure is gravitationally bound, whether the galaxies are actually connected by their motion, or just happen to be near each other in space. By mapping flows, Tully's team could identify which galaxies were genuinely part of the same dynamical system. If galaxies are flowing inward toward a common point, they're part of the same basin of attraction, regardless of how densely packed they appear on the sky. This is a fundamentally different way of defining structure in the universe. It also revealed something surprising. The old local supercluster, the structure centered on the Virgo cluster that astronomers thought we belonged to, isn't a separate entity. It's just a sub-region of Laniakea. We don't live in the Virgo supercluster. We live in the Laniakea Supercluster, on its outer edge, falling inward toward its center. The discovery of Laniakea answered a lot of questions. It explained why our motion through the universe is so fast and why it's directed toward the Great Attractor region. We're part of a massive supercluster, and we're falling toward its center like a galaxy caught in a gravitational whirlpool. But Laniakea also raised new questions, because when Tully's team mapped the boundaries of Laniakea, they found that the flows don't stop at the edge. Galaxies on the far side of Laniakea, the side away from us, are flowing inward. but galaxies just beyond the boundary are flowing outward, away from the Great Attractor, towards something else. There are external attractors, structures outside Laniakea that are pulling on galaxies just beyond our basin of attraction. And the biggest of these, the most massive structure in the nearby universe, is something called the Shapley Concentration, also known as the Shapley Supercluster. And here's the kicker. Laniakea itself is moving. The entire supercluster, all 100,000 galaxies, all 100 quadrillion solar masses, is flowing toward Shapley at several hundred kilometers per second. The Great Attractor isn't the final destination. It's a waypoint. We're falling toward it, yes, but it's falling toward something even bigger. And that something is where we're really headed. 650 million light years away, in the direction of the constellation Centaurus, lies the most massive structure in the nearby universe, the Shapley Supercluster, also called the Shapley Concentration. It's not just big, it's almost incomprehensibly massive, a gravitational monster that dominates everything within 500 million light years. Harlow Shapley, the American astronomer who first catalogued this region in the 1930s, recognized it as an unusual concentration of galaxies. He estimated it was about 14 times farther away than the Virgo cluster, which would place it at roughly 700 million light years with modern distance measurements. What he couldn't have known at the time was that he'd discovered the single most massive structure that would be found in the local universe for decades to come. The Shapley Supercluster contains over 20 massive galaxy clusters, each one comparable to or larger than the Virgo cluster. The core of the structure is dominated by 3 particularly rich clusters: Arbel 3558, Arbel 3562, and Arbel 3556. These 3 clusters alone contain thousands of galaxies, and they're so close together that they're interacting gravitationally, pulling on each other, distorting each other, possibly in the process of merging into a single supercluster. The total mass of the Shapley Supercluster is staggering. Estimates vary, but most put it at around 10 to the 16th solar masses. That's 1 followed by 16 zeros. To put that in perspective, it's about 10 times more massive than Laniakea. If Laniakea is a city, Shapley is a megalopolis. The volume it occupies is similarly vast. The supercluster extends more than 120 million light years across, roughly a quarter of the size of the observable universe. Its density excess, the amount by which it's overdense compared to the average universe, is about a factor of 4. That might not sound like much, but in cosmology, where the universe is remarkably smooth on large scales, a factor of 4 overdensity is enormous, and it's pulling us. In the 1980s and 90s, as astronomers mapped peculiar velocities across larger volumes, they realized that the motion of galaxies in our region wasn't fully explained by the Great Attractor. There was a significant residual velocity pointing beyond the Great Attractor, toward the Shapley region. Detailed studies of galaxy flows confirmed it. The Shapley Supercluster is so massive that its gravity extends across hundreds of millions of light years, influencing the motion of galaxies well outside its own boundaries. Our local group is falling toward Shapley at about 250 kilometers per second. The Virgo cluster is falling toward Shapley. The Great Attractor region is falling toward Shapley. The entire Laniakea Supercluster is flowing toward Shapley as part of a larger scale motion. It's like a whirlpool in the ocean, pulling in water from enormous distances. Shapley is the gravitational drain for our entire region of space. This is what's really happening. The 2 million miles per hour that we're moving through space isn't just one motion. It's a cascade of motions, each one embedded in the next. We're orbiting the center of the Milky Way. The Milky Way is falling toward the center of the local group. The local group is falling toward the Virgo cluster. The Virgo cluster is falling toward the Great Attractor. The Great Attractor is falling toward Shapley. It's gravity all the way down, Russian dolls of cosmic motion. But here's the catch. We're never going to get there. The universe is expanding. The Shapley Supercluster is receding from us due to the expansion of space at roughly 45,000 kilometers per second. That's over 100 million miles per hour. Our peculiar velocity toward Shapley, the real motion through space, is only a few hundred kilometers per second. We're falling toward Shapley, but we're not falling fast enough to overcome the expansion. The distance between us and Shapley is increasing, and it always will be. It's like running on a cosmic treadmill. You're sprinting forward at hundreds of kilometers per second, but the treadmill is moving backward at tens of thousands of kilometers per second. You make progress relative to the treadmill, but the destination keeps moving away faster than you can reach it. In a few billion years, as the expansion of the universe continues to accelerate due to dark energy, the expansion rate will increase. Structures that are not already gravitationally bound will be carried apart by the expansion faster and faster. Eventually, Shapley will recede from view, redshifted into invisibility, forever beyond our reach. Our journey toward it is doomed to failure, not by any deficiency in gravity, but by the fundamental expansion of space-time itself. But Shapley's influence doesn't end with its direct gravitational pull. Because Shapley sits in a particularly interesting location, it's part of a larger structure, a megastructure, that may represent one of the largest coherent features in the observable universe. And understanding that structure requires understanding the architecture of the cosmos on the largest scales. In January 2017, a team of astronomers led by Yehuda Hoffman from the Hebrew University of Jerusalem published a discovery that fundamentally changed how we understand our motion through space. They weren't looking for what's pulling us. They were looking for what's pushing us. For decades, the assumption had been that our motion through the universe was entirely driven by gravitational attraction. Dense regions, concentrations of galaxies and dark matter pull on us. The Great Attractor pulls, Shapley pulls. These attractors accelerate us through space like massive objects rolling downhill in the gravitational landscape of the universe. But the numbers didn't quite work. The direction of our motion, as measured by the CMB dipole, pointed not directly toward Shapley, but at an angle to it. And the magnitude of our velocity was slightly higher than could be explained by Shapley's pull alone. Something was missing from the picture. Hoffman's team took a different approach. They used the Cosmic Flows database, the same catalog of peculiar velocities that had revealed Laniakea, but they analyzed it in a new way. Instead of just mapping where galaxies are flowing toward, they mapped where galaxies are flowing away from, and they found something extraordinary. Directly opposite Shapley, on the other side of the sky, there's a region of space that is nearly devoid of galaxies. It's a void, a vast underdense region, where the density of matter is significantly lower than the cosmic average, and galaxies near this void are moving away from it at high velocities. They named it the Dipole Repeller. Now, to be clear, the Dipole Repeller isn't actually repelling anything. Gravity is always attractive. There's no such thing as negative mass or anti-gravity pushing galaxies away. What's happening is more subtle and in some ways more elegant. Imagine you're in a swimming pool. In one direction, there's a drain pulling water toward it. In the opposite direction, there's nothing, just the edge of the pool. If you release a floating object in the middle, it will move toward the drain. But here's the key insight. That motion is not just because of the pull from the drain. It's also because there's no pull from the opposite direction. The absence of mass on one side contributes to the net motion just as much as the presence of mass on the other side. The same principle applies to cosmic voids. In a perfectly uniform universe, every galaxy would be pulled equally in all directions, and the net force would be zero. But the universe isn't uniform. In regions where there's an overdensity, like Shapley, gravity pulls extra hard. In regions where there's an underdensity, like the Dipole Repeller, gravity pulls less than average. The difference creates a net force. Galaxies in between a massive overdensity and a massive underdensity experience a push-pull effect. They're pulled strongly toward the overdense region and pulled weakly away from the underdense region. The result is a net acceleration toward the overdensity that's larger than you'd expect from the overdensity alone. The void amplifies the effect. The Dipole Repeller is located approximately 700 million light-years away, in the direction of the constellation Eridanus and Cetus. It's roughly the same distance as Shapley, but in the opposite direction. Its size is comparable to that of a supercluster, perhaps 200 million light-years across, but it contains almost no galaxies. Observations at optical, infrared, and radio wavelengths confirm it. There's just not much there. The mass deficit in the Dipole Repeller is estimated to be comparable in magnitude to the mass excess in Shapley. In other words, the absence of matter in the repeller has roughly the same gravitational effect as the presence of matter in Shapley. The two structures, one overdense and one underdense, form a dipole, a two-pole system that drives the bulk flow of galaxies in our region, and we're caught in the middle. The Milky Way sits roughly between the Dipole Repeller and the Shapley Attractor. We're being pulled toward Shapley by its enormous mass, and we're being pushed away from the Dipole Repeller by its enormous lack of mass. The combination of these two effects explains both the direction and the magnitude of our motion through the universe. This is profound. It means that understanding cosmic motion requires understanding not just where the galaxies are, but where they aren't. Voids matter. Empty space, or rather space that's emptier than average, has a gravitational signature. It shapes the flow of matter on the largest scales just as much as dense clusters and superclusters do. The discovery of the Dipole Repeller also has implications for how we think about the large-scale structure of the universe. The cosmic web, the network of filaments and voids that defines the distribution of matter, isn't static. It's dynamic. Galaxies flow along the filaments, accelerating away from voids and toward dense nodes. The entire structure is in motion, a vast, slow-motion dance governed by gravity, and our participation in that dance, our 2 million mile-per-hour journey through space, is the result of this cosmic choreography. We're not just being pulled by Shapley, we're being pushed by the void behind us. Both forces are necessary to explain where we're going and how fast we're getting there. Remove either one, and the story falls apart. To understand why voids and overdensities exist, why the universe is structured the way it is, we need to go back to the beginning. Not to the Big Bang itself, but to what happened immediately after. In the first trillionth of a trillionth of a trillionth of a second, after the Big Bang, the universe underwent a period of exponential expansion called cosmic inflation. space itself expanded faster than the speed of light, doubling in size over and over again in an incomprehensibly brief moment. This inflation smoothed out any large-scale irregularities that might have existed, stretching them beyond the observable horizon. But inflation couldn't smooth out everything. At the quantum level, the universe is fundamentally uncertain. Quantum mechanics tells us that fields, including the space-time field itself, undergo random fluctuations. These fluctuations are tiny, microscopic variations in energy density that exist even in a vacuum. Under normal circumstances, they appear and disappear in fractions of a second, too small to notice. But during inflation, these quantum fluctuations were stretched. As space expanded exponentially, the fluctuations were pulled from subatomic scales to cosmic scales. By the time inflation ended, these quantum ripples had been frozen into the fabric of space as tiny variations in density. Some regions were slightly denser than average. Others were slightly less dense. These density variations were incredibly small, less than 1 part in 100,000. If you could see the universe 380,000 years after the Big Bang, when it became transparent and released the cosmic microwave background radiation, it would look almost perfectly uniform. But almost isn't perfectly. The CMB contains tiny temperature fluctuations, hot spots and cold spots, that correspond to these density variations. NASA's Planck satellite has mapped them with exquisite precision. They're real, and they're the seeds of everything that came after. Gravity amplifies density differences. Regions that were slightly denser than average had slightly stronger gravity. They attracted more matter from their surroundings. As matter fell into these regions, they became even denser, and their gravity became even stronger. This is called gravitational instability, and it's a runaway process. The rich get richer. Over hundreds of millions of years, the overdense regions collapsed under their own gravity, forming the first stars, the first galaxies, and eventually the first clusters of galaxies. The underdense regions, meanwhile, emptied out. Matter flowed away from them, toward the overdense regions, leaving behind vast voids. By about 1 billion years after the Big Bang, the large-scale structure of the universe had taken shape. The distribution of matter resembled a sponge or a foam. Dense filaments of galaxies stretched across space, connected at nodes where galaxy clusters formed. Between the filaments were voids, enormous empty bubbles containing almost no galaxies. This structure is called the cosmic web. It's the dominant feature of the universe on scales larger than a few 100 million light-years, and it's remarkably stable. The filaments and voids persist for billions of years, slowly evolving as gravity continues to pull matter along the filaments toward the densest nodes. The statistics are staggering. Roughly 90% of the volume of the universe is voids. Most of space is empty, or nearly empty. Galaxies are confined to the filaments, the thin threads that make up only 10% of the volume. We live on a filament, embedded in a sheet of galaxies that includes Laniakea and other nearby superclusters. The typical void has a diameter of about 100 to 300 million light-years. The largest known voids are even bigger. The Boötes void, discovered in 1981, spans about 330 million light-years and contains only a few dozen galaxies in a volume that should contain thousands. It's almost perfectly empty, a cosmic desert. Filaments, on the other hand, can stretch for hundreds of millions of light-years. The longest structures in the universe are filament complexes, chains of superclusters connected by bridges of galaxies. The Sloan Great Wall, discovered in 2003, extends over 1.3 billion light-years. It's not a single object, but a vast sheet of galaxies, part of the cosmic web's skeletal framework. And all of this, every filament, every void, every supercluster, traces back to those quantum fluctuations in the first moment after the Big Bang. The largest structures in the universe today are the direct descendants of microscopic quantum uncertainty inflated to cosmic scales. It's one of the most profound connections in all of physics, linking the smallest and largest scales of nature through a single coherent theory. But the cosmic web isn't static. It's dynamic, in motion, evolving. Galaxies flow along the filaments, accelerating toward the nodes. Voids expand as the universe expands, pushing galaxies away from their centers. The entire structure is a vast, slow-motion fluid, driven by gravity and the expansion of space. Our motion through the universe, our 2 million mile-per-hour journey toward the Shapley Concentration, is part of this flow. We're moving along a filament, accelerating away from the Dipole Repeller void and toward the Shapley node. We're surf riding on a wave of space-time, carried by the largest currents in the cosmos. And this is the deepest answer to the question of what we're moving toward. We're not just moving toward Shapley, we're moving through the cosmic web, following the gravitational contours laid down 13.8 billion years ago by quantum fluctuations smaller than an atom. We're part of the structure of the universe itself. In 2008, a NASA astronomer named Alexander Kashlinsky made an announcement that shook the cosmology community. He and his team had discovered something that shouldn't exist. Using data from the Wilkinson Microwave Anisotropy Probe, WMAP, they'd analyzed the motion of over 700 galaxy clusters spanning billions of light years, and they found that these clusters, spread across enormous distances, were all moving together in the same direction at over 2 million miles per hour. They called it the dark flow. The motion wasn't random. It wasn't caused by local gravitational effects like the pull of Shapley or the push from the Dipole Repeller. It was a coherent, large-scale flow affecting clusters out to distances of 2.5 billion light-years, all streaming toward a patch of sky between the constellations Centaurus and Vela. And crucially, the velocity didn't decrease with distance. Clusters billions of light-years away were moving just as fast as clusters nearby. This was deeply troubling. According to the standard cosmological model, the universe should be homogeneous on large scales. The cosmic microwave background, the relic radiation from the Big Bang, is incredibly uniform, varying by less than 1 part in 100,000 across the sky. This uniformity implies that the universe should look roughly the same in all directions, especially on scales of billions of light-years. But the dark flow suggested otherwise. It implied that there was structure, enormous structure, capable of exerting gravitational influence across billions of light-years. And the only way to explain such a large-scale coherent motion was if that structure lay outside our observable universe. The observable universe has a radius of about 46 billion light-years. That's the distance light has been able to travel since the Big Bang, accounting for the expansion of space. Anything farther away is beyond our cosmic horizon. We can't see it. We can't detect it. Light from those regions hasn't had time to reach us yet, but that doesn't mean those regions don't exist. The universe beyond the horizon is presumably filled with matter and structure, just like the universe we can see. And if there's a concentration of matter out there, something truly enormous like a super Shapley or a mega supercluster, its gravity would affect us. Gravity has no horizon. It propagates at the speed of light, but gravitational effects from the past can influence us today, even if the sources are now beyond our visibility. Kashlinski's proposal was that the dark flow is caused by structures beyond the observable universe, possibly hundreds of billions of light-years away. Relics of the universe's earliest moments that inflation pushed beyond our horizon. These structures could be massive concentrations of matter, perhaps even exotic forms of space-time or connections to other inflationary bubbles, other universes in a multiverse. It was a radical idea. It challenged the Copernican principle, the notion that we don't occupy a special place in the universe. If there's a massive structure beyond the horizon pulling on us, then our observable universe isn't representative of the universe as a whole. We're in a special location, caught in the gravitational influence of something we can never see. The cosmology community was skeptical. Detecting such subtle motions requires incredibly precise measurements, and there are many sources of error. The technique Kashlinski used, analyzing the kinematic Sunyaev-Zeldovich effect, where hot gas in galaxy clusters scatters CMB photons, is powerful but challenging. Small systematic errors can mimic a bulk flow. In 2010, Kashlinski's team published a follow-up paper using more data, increasing the sample to over 1,000 clusters. They confirmed the dark flow, extending its reach even farther, but doubts persisted. Then, in 2013, the Planck satellite, which measured the CMB with far greater precision than WMAP, weighed in. The Planck team analyzed the same clusters using the same technique. Their conclusion was definitive. They found no evidence of a bulk flow larger than about 160 kilometers per second, well below Kashlinski's claimed velocities. If the dark flow exists, it's much weaker than originally reported. Or it doesn't exist at all. Subsequent studies have supported Planck's findings. Independent analyses using different datasets and different methods have failed to confirm the dark flow at the amplitudes Kashlinski reported. The consensus today is that the original claim was likely the result of systematic errors or subtle biases in the analysis. But the story doesn't end there. Because while the specific dark flow claim has been largely debunked, the broader question remains: are there structures beyond the observable universe? And if so, can they influence us? The answer to the first question is almost certainly yes. There's no reason to think the universe stops at our horizon. Inflation predicts that the universe extends far beyond what we can see, possibly infinitely. And if the universe is infinite, then every possible structure, no matter how large, exists somewhere. The answer to the second question is more subtle. Gravitationally, structures beyond the horizon can influence us, but only if they formed before inflation ended. Inflation erases causal connections. Regions of space that were once close enough to interact gravitationally are pushed apart so rapidly that they lose contact. By the time inflation ends, only structures within a limited region, what becomes our observable universe, can affect each other. But there's a loophole. If there were pre-inflationary structures, density variations that existed before inflation began, they could be stretched to enormous sizes. Part of such a structure might lie within our horizon, and part might lie beyond. The gravitational effect of the entire structure, including the parts we can't see, could influence the motion of galaxies within our observable universe. This is speculative, pushing the boundaries of what we can test with current observations. But it's not impossible. And it highlights a profound truth. The universe we see is not necessarily the universe that exists. There are limits to observation, horizons beyond which we cannot peer. And somewhere out there, beyond the edge of the observable cosmos, there might be structures so vast they dwarf everything we know, pulling on us with gravity we can measure but never fully explain. There's a fundamental limit to what we can measure about the universe. It's not a limit of our telescopes or our instruments. It's a limit written into the fabric of space-time itself. The universe is expanding. The farther away a galaxy is, the faster it's receding from us due to the expansion of space. At some distance, typically around 300 to 500 million light-years depending on direction, the expansion velocity becomes larger than any reasonable peculiar velocity, any real motion through space caused by gravity. Beyond that threshold, expansion dominates. The cosmic flow becomes impossible to disentangle from the Hubble flow. This is the horizon of peculiar velocity measurements. We can map the motions of galaxies out to a few 100 million light-years with reasonable confidence. Beyond that, the signal drowns in the noise of expansion. We're like cartographers trying to map ocean currents while the entire ocean is rising. Close to shore, we can measure the flow. Far from shore, all we see is the tide. This matters because it means there could be structures beyond our measurement horizon that influence us but remain invisible. Shapley, at 650 million light-years away, is near the edge of what we can map. We see its gravity affecting galaxies within a few 100 million light-years of it. But beyond that, the trail goes cold. If there's something even larger, even farther away, we might never map it directly. The concept of basins of attraction helps us understand what we can and cannot know. A basin of attraction is a region of space where all the galaxies are flowing toward a common gravitational center. It's defined dynamically by motion, not by density. Two galaxies can be part of the same basin, even if they're separated by a void, as long as they're both flowing toward the same attractor. Laniakea is a basin of attraction. Everything within its boundaries, roughly 500 million light-years across, is flowing toward the Great Attractor at its center. The boundaries are watersheds, places where the flow changes direction. On one side of the boundary, galaxies flow inward toward Laniakea. On the other side, they flow outward toward neighboring basins. In 2024, an international team led by astronomers from the University of Hawaii and the Hebrew University published a study mapping the basins of attraction in the local universe with unprecedented detail. They used the Cosmic Flows 4 catalog, which contains distances and velocities for over 56,000 galaxies, and applied advanced algorithms to identify the gravitational landscape. What they found surprised everyone. The Shapley Basin is enormous, but it's not the largest. The Sloan Great Wall, a vast filament complex spanning over 1 billion light-years, turned out to have a basin of attraction with a volume of about 500 million cubic light-years, more than twice the size of Shapley's Basin. And here's the kicker. The Milky Way, previously thought to reside firmly within the Laniakea Basin, might actually be part of the Shapley Basin. The watershed boundary between Laniakea and Shapley is complex and uncertain. And depending on how you define it, we could be on either side. This is profound. It means our understanding of which structure we belong to, where we're ultimately headed, is still evolving. The more we measure, the more complex the picture becomes, structures nest inside other structures. Flows merge and diverge. The cosmic web is not a simple hierarchy, but a tangled, multi-scale network. And there are limits to how far we can ever map it. Beyond about 1 billion light-years, the expansion of space carries galaxies away from us at velocities approaching the speed of light. Peculiar velocities, typically a few hundred kilometers per second, become negligible compared to recession velocities of tens of thousands of kilometers per second. The map fades to white noise. But even within the mappable universe, there are mysteries. Some regions of the flow don't match expectations. The amplitude of bulk flows on large scales, the coherent motion of many galaxies in the same direction, is sometimes larger than standard cosmological models predict. This was the motivation behind the dark flow hypothesis, and while that specific claim has been debunked, the broader issue remains. The universe on scales of hundreds of millions of light-years is lumpy, more structured than a perfectly smooth initial state would suggest. This could be explained by cosmic variance. We live in one particular region of the universe, and that region might be slightly more overdense or underdense than average. The structures we see around us, Laniakea, Shapley, the Dipole Repeller, might not be representative of the universe as a whole. We're sampling one watershed, one drainage basin, and from within it, we can't see the entire river system. Or it could be a hint of something deeper. Perhaps the initial conditions of the universe, the quantum fluctuations that seeded all structure, were not perfectly Gaussian. Perhaps there were subtle correlations, non-random patterns, that led to the formation of exceptionally large structures. If so, studying the largest basins of attraction could reveal information about the physics of inflation, the first moment of the universe's existence. But we're approaching the limit of what observation can tell us. The cosmic horizon is both an observational limit and a theoretical one. We can't see beyond it, and more fundamentally, we can't be causally connected to it. Regions of the universe more than about 46 billion light-years away are beyond our horizon. Light from those regions hasn't had time to reach us. Gravitational influences from those regions, while they propagate at the speed of light, can't affect us today unless they were set in motion billions of years ago. This is the final answer to what we're moving toward. Within the observable universe, we're moving toward the Shapley Concentration, pulled by its gravity and pushed by the Dipole Repeller. But beyond the observable universe, there could be structures we'll never see, never measure, never fully understand. Our motion through space is the result of all these influences layered on top of each other, stretching back to the origin of the cosmos. And that's as far as we can go. The rest is speculation, mathematics, and philosophy. There is no such thing as standing still. That's the first lesson of our cosmic journey. When you sit in a chair, you think you're stationary. You feel at rest, but you're not. You're spinning with the Earth at over 1,000 miles per hour. You're orbiting the Sun at 67,000 miles per hour. You're racing through the galaxy at 500,000 miles per hour. And you're rushing through the universe at over 2 million miles per hour toward the Shapley Concentration. Every measurement we make reveals another layer of motion. Every scale we examine shows us another current in the cosmic ocean. From the rotation of our planet to the flow of superclusters, we are always, inescapably, in motion. But here's the deeper truth. That motion isn't random. It's structured. It's choreographed. Our journey through space at 2 million miles per hour is the result of a gravitational dance that began 13.8 billion years ago with quantum fluctuations smaller than an atom. Those fluctuations were stretched by cosmic inflation to fill the universe. They became the seeds of galaxies, clusters, superclusters, and voids. They created the cosmic web, the vast scaffolding of matter that defines the architecture of everything. We live on a filament of that web. We're embedded in the Laniakea Supercluster, flowing along with 100,000 other galaxies toward the Great Attractor at its heart. But the Great Attractor is itself part of a larger flow. Laniakea is falling toward the Shapley Concentration, the most massive structure in our corner of the universe. And behind us, pushing us along, is the Dipole Repeller, a vast cosmic void whose absence of matter creates a gravitational pressure as real as any pull. This is what we're moving toward. Not just Shapley, not just a single destination. We're moving through the structure of the universe itself. We're riding the currents of space-time, following paths laid down at the dawn of creation, and will never arrive. The expansion of the universe guarantees that. Shapley is receding from us faster than we're falling toward it. The cosmic treadmill runs backward at 100 million miles per hour, and our 2 million mile per hour sprint isn't enough to overcome it. In billions of years, as dark energy drives the expansion to accelerate, Shapley will fade beyond the horizon, redshifted into invisibility, forever out of reach. But that doesn't make the journey meaningless, because the journey is what defines us. For billions of years, humans wondered about their place in the cosmos. We invented myths to explain the stars. We imagined that Earth was the center of everything, that the heavens revolved around us. Then Copernicus showed us we orbit the sun. Shapley, Harlow Shapley, showed us the sun orbits the galaxy. Hubble showed us the galaxy is one of billions, scattered through an expanding universe. And now, in the 21st century, we've mapped the flows that carry us through that universe, revealing that even on the largest scales, we are part of something greater. This is perhaps the most profound shift in perspective in human history. We are not observers standing apart from the cosmos, looking at it from the outside. We are participants, embedded within it, moving with it, shaped by it. The atoms in our bodies were forged in stars. The calcium in our bones, the iron in our blood, came from supernovae that exploded billions of years ago, scattering their enriched material into space where it eventually coalesced into planets and life. We are made of stardust, and we are traveling through the universe alongside those stars, all of us falling together toward the same gravitational centers. There's a strange comfort in this, to know that you're not in control, that the forces governing your motion through space are incomprehensibly vast and ancient, is to understand your place in the grand scheme. You are small, yes. Your life is brief, a flicker against the backdrop of cosmic time. But you are also connected to everything. The same gravity that holds you to your chair is pulling your galaxy through space at 2 million miles per hour. The same quantum fluctuations that seeded the cosmic web gave rise to the planet you live on, the sun that warms you, the structures that surround you, and the motion continues. Long after humanity is gone, if we are ever gone, the Milky Way will continue its journey. It will merge with Andromeda in 4 billion years, forming a new galaxy that will still be part of the flow toward Shapley, still embedded in the cosmic web. The dance will continue without us, as it has continued for billions of years before us. But here's the beautiful part. We get to witness it. We get to measure it. We are the part of the universe that has become conscious of its own motion, that can trace the flows and map the structures and ask the question, what are we moving toward? The answer, in the end, is ourselves. We are moving through a universe that is our home, following paths written into the fabric of reality at the moment of creation. We're navigating a cosmic river whose currents connect the smallest scales to the largest, the quantum to the cosmological, the beginning to the end. There is no destination. There is only the journey. And the journey, in all its incomprehensible scale and beauty, is what it means to exist in this universe.